So let's see. We're in section 3.5. So this is the last thing we're talking about this chapter. We're talking about exponential growth and decay. So they're just two basic models that we're going to talk about in this section. Two types of functions that we're going to work with. We're either going to be working with y equals a e to the bx, where b is greater than 0, and this is going to be our growth, exponential growth.
What's greater than 0?
Sorry, b. So our exponent is going to be positive when we have a positive exponent, exponential growth. And if just a quick graph, just a reminder of what exponential growth looks like. Our exponential growth looks like that, if this is our x and y axis. And remember, our exponential function, if it's not shifted, always goes through the point 0, 1. So this is going to be our growth, what we call our growth model. Our second one, it's the same form. Our decay model, y equals a e to the bx, where b is less than 0. And this is decay. So our exponent is going to be negative. And our quick graph of exponential decay. Our exponential decay looks like this. And it also goes through the point 0, 1. And we're going to be solving equations involving growth or decay with some different applications. Our different applications, exponential growth or decay, have to do with populations, like bacterial growth. Populations of cities usually follow an exponential growth model. Interest, we've talked about interest already. Compound interest is an exponential growth, we hope. Depreciation would be exponential decay. So as you buy your car and it loses value, that's going to be usually an exponential decay model. And radioactivity is also a exponential model. So those are some of the things that we're going to model with these equations. So we're just going to go through some examples of how we use these equations, solve these equations for problems having to do with growth and decay. So our first one is population growth. So we say that we have a city. So our population in millions is modeled by y equals 1.8 e to the 0.026x, where y is the population and x is the time. So at time 0, if I plug in time 0 in for x, e to the 0 is 1. So our population at time 0 is just 1.8 times 1, or 1.8 million. So at x equals 0, I'm going to say the population, that's what this model tells us, the population equals 1.8 million. So we want to use this model to figure out what year will the population exceed or reach, what year will the population reach 2.6 million? And x equals 0 corresponds to the year 1980. So that's when we start measuring using this model. So our question is, what year will the population be 2.6 million? So we want to solve for x in our population, in our growth model. So we're going to plug in 2.6 million for our population. So I'm going to say 2.6 equals 1.8 e to the 0.026 x. And we have to solve for x. So in order to solve this, just like we've done with our other exponential equations, we want to get the exponential function by itself on one side. So I'm going to divide both sides by 1.8. And I'm going to turn this around. So e to the 0.026 equals 2.6 divided by 1.8. And I'm going to change this. I don't want my population to be 2.6 million. I want it to be 2.5 million. Sorry.
Why did you change it?
Because the example that I did used 2.5, so my answer would have been 2.5. I just miswrote my number. So when we get our exponent, we have an x here. When we get our exponential function on one side and a number on the other, how do we solve this now? Take the natural log of both sides. So I'm going to say the natural log of e to the 0.026x equals the natural log of 2.5 over 1.8. So the natural log and the exponential function are inverses, so they undo each other. So 0.026x equals the natural log of 2.5 over 1.8. And to get x by itself, I'm just going to divide by 0.026. And when I plug this into my calculator, natural log of 2.5 divided by 1.8, all divided by 0.026, I get about, we'll say, about 12.6 years. So our population would reach 2.5 million in about halfway through 1992. So we add 12.6 to 1980. Questions on that? Yes?
Where did you know the 1980 came from?
The problem would give you that t equals 0, our first measurement corresponds to the year 1980. So your problem would give you that. So just using the methods that we've worked with before, applying it to a population growth model. All right, our next example is a little more complicated. So, and there are a couple of problems like this on the homework, so make sure you're following along with what we're doing. So we have a bacterial growth. And we can model bacterial growth with an exponential model. So our problem says we start our experiment after 2 hours. The population is The population is 256. And then 5 hours after that, after another 5 hours, the population equals 541. We want to know the population after 24 hours. Now, we're going to, our bacterial growth is an exponential model. So our model is going to be y equals ae to the bx. We don't know a or b. We're going to have to use our numbers that they're giving, that we're given, to figure out a and b. So what we're going to do is we're going to plug in our first set of numbers and solve for a. So our first step on this problem, we're going to use our first set of numbers to find a. So I'm going to plug in our population. Y is the population. We'll put that over here. Y equals population, x equals time. So plug in our first set of numbers. 256 equals ae to the b times 2. And I want to use this first set of numbers to find a. Yes?
Wait, the 2 from the 2 hours?
2 is from the 2 hours, yes. So our population is 256, our time is 2 hours. So we're going to use this. Now I want to get a by itself, so I'm going to divide both sides by e to the b times 2. I'm going to turn this around and say a equals 256, and an exponent in the denominator, a positive exponent in the denominator. How else can I write that? My exponent is positive in the denominator. What can I do with that exponent? Negative in the numerator. So I'm going to bring it to the top, and I'm going to write this as e to the minus 2b. The positive exponent in the denominator is the same as a negative exponent in the numerator. So a equals 256 times e to the minus 2b. So I figured out what a is. Now my second step is I'm going to plug this a in a into my equation. With the second point to find b.
Wait, so how did you can just like make it negative because it's dividing by?
Yes, so a positive exponent in the denominator is the same as a negative exponent in the numerator. So I just made it negative 2b rather than over e to the 2b. So now we're going to plug a into our original equation with our second point and use that to find b. So I'm going to use this equation with this as a. So I'm going to say, before I plug my points in, I'm going to write my equation. So y equals, this is a. I'm going to put that in here for a. 256.
Isn't it 541 equals?
I'm not plugging in numbers yet. I'm just going to plug this value of a into this equation. And then we'll plug in numbers. So a is 256 e to the minus 2b. That's my a, and I'll put this here. This is a. Times e to the bx. So I'm just substituting this value of a in to this equation. Now we're going to simplify this. Y equals 256. When I multiply two numbers, the same number raised to two different exponents, what do I do with the exponents? Add them. So I get 256 e to the 2b minus b is bx. I'm multiplying e to the minus 2b. Sorry, I did my addition wrong. This 2b,
Negative.
this would be minus 2b plus bx.
So it'd be negative bx.
This one doesn't have an x with it.
Oh.
So minus 2b plus bx is just minus 2b plus bx. I'm adding the exponents. When I multiply these two numbers raised to an exponent, I add the exponents. So minus 2b plus bx. Now we're going to plug in our numbers. This is my model, and I'm going to plug in my second point. So my second point is 541, and x is 5. So I get 541 equals 256 e to the minus 2b plus b times 5. Now we can add these two together. Yes?
So you'd go, isn't it after another 5 hours, so you'd be at hour 7?
What I'm doing is I'm taking this value for a,
Yeah.
and I'm not going forward. I'm using this value of a back into my original equation.
Okay.
So we don't have to worry about that additional 2 hours. This is whatever a is going to work in this equation for any time x. Okay? So I'm just going back to my original equation. I'm not going back to here. I'm going all the way back to the very beginning. Okay? So now I'm going to write 541 equals 256 e minus 2b plus 5b is what? 3b. E to the 3b. Now I can solve for b. I have an exponential equation. I have one variable here. So I can get this exponential function, exponential expression by itself, and solve for b. So I'm going to divide by 265.
Isn't it 256?
256, thank you. I switched those around. And I'm going to turn this around, so e to the 3b equals 541 over 256. Now how do I get rid of this exponent? Take the natural log of both sides. We know how to do that. So the natural log of e to the 3b equals the natural log of 541 over 256. So 3b equals the natural log of 541 over 256. And I can divide both sides by 3. So b, finally, you notice a lot of steps. b equals the natural log of 541 divided by 256, all divided by 3. And if I plug that into my calculator, just to get some numbers so I don't have to write this over and over, b is about 0.2494. So now we found b. So we're almost ready to solve our problem. Let's scroll back up. Here we said a, we found that a was 256 times e to the minus 2b. Well, now we know we have a number for b. We can plug b into this equation and find a. Get a number for a. I'm going to plug b back in here. So my third step, I'm going to plug in b to find a. So my original equation says that a equals 256 when we solve for a. E to the minus 2 times 0.2494. I can calculate this out. I can plug this into my calculator, and when I calculate this out, I get the A is about 155.4583. And when we do these exponential models and growth and decay, we want to keep several decimal points, because if you round off, if I rounded this off to 155.5, my final answer could end up being way off. Yes.
So you just entered in 256E, like into your calculator, you just entered in that A into your calculator.
Yes. So I just plugged this into my calculator. Okay. So A equals about 155.4583. Now I have A and B for my exponential model. My original model was y equals a e to the bx. I know A and I know B, so now I have my equation. So finally, we can say y equals A 155.4583 e to the 0.2494 x is our growth model for this bacterial growth. And our problem asked us, the original problem that we were asked to solve is what is the population after 24 hours? If we go clear back to the top, it says what's the population after 24 hours. So we had to do all these intermediate steps before we could even get to that. So now we plug in 24 for our time. So we get y equals 155.4583 e to the 0.2494 times 24. And I can put that into my calculator, and I finally end up with y equals, I come up with 61819.71. So after 24 hours using this growth model, our bacterial population would be over 61,000, almost 62,000 bacteria. Now, thankfully, there's only a couple of these in your homework. Like two, where you have to use 2 points to find your exponential equation. And the process is the same. You use the first point, use the first set of points to find A, plug that back into your original equation, and use the second points to find B to get your equation. I know that was a lot of steps, but just follow. If you just follow along with this procedure, it's not extremely complicated. Just a fair amount of work. Questions on that problem? I'm not going to dwell a lot on that, because most of our problems are not these, or other kinds of problems. All right, let's look at a couple of examples using interest, compound interest, and then we'll be done. So just a couple of reminders about compound interest. Most of your problems have to do with compound interest. So we talked about compound interest right at the beginning. I just want to remind you what our compound interest formulas were. So our first one, if we have compounding periods, A equals P 1 plus R over N to the NT. A equals our amount after some time. P is our original amount. R is the annual interest rate. annual as a decimal N is our compounding periods per year. And T is time. In years, usually in years.
Can it be in anything else?
It could be in anything else as long as our annual interest rate and our compounding periods corresponded to our time. So if our annual interest rate is in years, we'd have to express our time in years and our compounding periods in years. So all the units have to match essentially.
So if you go from years to months, you just divide the compound by 12 or something?
Right. And your interest rate, so you'd have to talk about a monthly interest rate and compound periods per month.
Yeah.
And our continuous interest, continuous compounding, is A equals PE to the RT. So this is for continuous compounding. And we've worked some problems that involve each of these already. I just want to do a couple of examples of problems like you might see in your homework today. All right, so let's look at a couple of examples using compound interest. Let's say we have, this is for continuous, we have continuous compounding. And our principal, we're starting with $5,000. And our amount, we end up with, after 10 years, equals I want this to be 500, not 5,000. And our amount after 10 years is $1,505. We want to figure out what was our interest rate. If we start with $500 and after 10 years we want $1,505, what interest rate do we have to invest our money at in order for that to happen? So on all of these kinds of problems, plug in what you have and solve for what you don't have. So I'm going to say that our amount, we're going to use A equals PE to the RT. And that gives us 1,505 equals 500 E to the R, and my time is 10. And I'm trying to solve for R. So this should look familiar by now. We've done several examples like this. I'm going to divide both sides by 500. I want to get the exponential expression by itself. So 1,500 divided by 500 is 3.01. I'm going to turn this around. This is E to the 10R equals 3.01. Now to get rid of this exponent, I'm going to take the log of both sides, natural log. So 10R equals the natural log of 3.01. The exponent and the logarithm are inverses, so they undo each other. And R finally is the natural log of 3.01 divided by 10. And I come out with 0.11 or 11%. So we'd have to invest our money at 11% in order to get $1,505 out of $500 in 10 years. But we solved this just like we solved other exponential equations. Questions on that example? All right, let's look at an example without continuous compounding, just to work with that formula.
Sorry, the answer to the last one was 0.11?
0.11 or 11%. So we want how much? We want to know how much to invest at 7.5%. Compounded monthly. To have $500,000 after 20 years. So we want to figure out how much we need to invest to end up with $500,000 in 20 years. And we're investing at 7.5% compounded monthly. So we're going to plug into our formula and solve for the part that we don't have. So we're not compounding continuously. So we're going to say our amount, 500,000, equals some principal that we're starting with times 1 minus our rate as a decimal point, interest rate, 0.075, divided by our compounding periods per year, 12, compounding monthly, to the 12 times 20.
Why is it a negative?
Sorry, that should be plus. You're right. And we're trying to solve for P. Now, when you do this compound interest formula, depending on your interest rate, this number can be very small. It can be like 1.0001 something. You can't round it to 1. You have to keep your decimal points to have an accurate answer. So when I calculate this out, calculating this in my calculator. I get 500,000 equals P times 1.00625 to the 12 times 20 is 240. I'm just going to write that as 240. So we need to keep these decimal points. If you round it off here, your answer could be off by several $1,000s. So you need to keep several decimal points to be accurate. And all I'm doing here is solving for P. So I can put this into my calculator, raise it to the 240th power, and divide both sides, and I get P by itself. So when I put this in my calculator, I get 500,000 equals P times 4.46082. I'm keeping a bunch of decimal places so that my answer is accurate. And I'm going to divide both sides by 4.46082 and calculate that out. And I end up finding that my principal has to be about $112,000 in order to have $500,000 after 20 years at 7.5% compounded monthly. So
Can you use that equation for annual too?
yes, if you're compounded annually, your n would just be 1.
Right.
Yeah. All right, any questions? Okay. Homework?
Oh, that's the great.
There you go.